the observation that a 115/230 volts main breaker is not suitable for a one-phase 230 volts ungrounded service is correct. The voltage rating of a breaker should always match the voltage of the electrical system that it is protecting. In a one-phase 230 volts ungrounded system, there is a single live wire, also known as the hot wire, and a neutral wire. The voltage between the live wire and the neutral wire is 230 volts. A 115/230 volts breaker is designed to protect a system where the voltage between the live and neutral wires can be either 115 volts or 230 volts. However, in a one-phase 230 volts ungrounded system, the voltage is always 230 volts. This means that the 115 volts rating of the breaker is not sufficient to protect the system. Using a 115/230 volts breaker in a one-phase 230 volts ungrounded system can result in several problems. Firstly, the breaker may trip prematurely when the system is operating at 80% load. This is because the breaker is not rated for the full 230 volts. Secondly, the breaker may not be able to properly protect the system from electrical overloads, which can lead to overheating and electrical fires. Thirdly, the breaker may trip even when the system is operating normally, causing unnecessary disruptions, also known as nuisance tripping. To resolve this issue, the 115/230 volts main breaker should be replaced with a 230 volts or 230/480 volts breaker that is rated for the appropriate amperage. This will ensure proper protection and prevent nuisance tripping. The importance of using correctly rated breakers cannot be overstated. Electrical systems are designed with specific voltage and current requirements, and using components that do not meet these requirements can lead to dangerous situations. A breaker's primary function is to protect the electrical system from overcurrents, which can be caused by short circuits, overloads, or ground faults. When a breaker detects an overcurrent, it trips, interrupting the flow of electricity and preventing damage to the system. If a breaker is not rated for the correct voltage, it may not be able to trip quickly enough or at the correct current level, which can result in damage to equipment, electrical fires, or even electrical shock. In the specific scenario of a one-phase 230 volts ungrounded system, using a 115/230 volts breaker creates a mismatch between the breaker's rating and the system's operating voltage. The 115 volts rating on the breaker indicates the voltage at which the breaker is designed to trip under certain overcurrent conditions. When the system operates at 230 volts, the breaker is effectively being subjected to twice the voltage it was designed for. This can cause the breaker to trip prematurely or, in some cases, fail to trip altogether when an overcurrent occurs. The consequences of using an incorrectly rated breaker can be severe. Overheating of electrical components is a significant risk. When a breaker is subjected to a voltage or current beyond its rating, it can overheat, which can damage the breaker itself and the surrounding wiring. This overheating can lead to insulation breakdown, creating a fire hazard. Electrical fires are particularly dangerous because they can spread quickly and are difficult to extinguish. Additionally, using an incorrectly rated breaker can compromise the safety of the electrical system. The breaker may not be able to effectively protect against electrical overloads, which can damage equipment and create a risk of electrical shock. If a fault occurs in the system, the breaker may not trip quickly enough to prevent damage or injury. To ensure the safety and reliability of an electrical system, it is essential to use breakers that are properly rated for the voltage and current requirements of the system. When selecting a breaker, it is important to consider the system's voltage, the expected load, and any applicable electrical codes or standards. In the case of a one-phase 230 volts ungrounded system, a breaker rated for 230 volts or 230/480 volts is appropriate. The 230/480 volts rating indicates that the breaker is suitable for use in systems with voltages up to 480 volts, but it will still provide adequate protection in a 230 volt system. In addition to the voltage rating, it is also important to consider the amperage rating of the breaker. The amperage rating indicates the amount of current that the breaker can safely carry before tripping. The amperage rating should be selected based on the expected load of the circuit. It is important to ensure that the breaker is not overloaded, as this can cause it to trip prematurely or fail to trip altogether. When replacing a breaker, it is always a good idea to consult with a qualified electrician. An electrician can help to ensure that the replacement breaker is properly rated for the system and that it is installed correctly. Additionally, an electrician can inspect the electrical system for any other potential problems, such as loose wiring or damaged components. In summary, using a 115/230 volts breaker in a one-phase 230 volts ungrounded system is not appropriate and can lead to several problems, including premature tripping, electrical overheating, and nuisance tripping. To resolve this issue, the breaker should be replaced with a 230 volts or 230/480 volts breaker that is rated for the appropriate amperage. It is important to always use breakers that are properly rated for the voltage and current requirements of the system to ensure the safety and reliability of the electrical system. Replacing the breaker requires turning off power to the circuit. Locate the main breaker panel and identify the breaker that controls the circuit with the air conditioning units. Turn the breaker to the OFF position. This will de-energize the circuit and make it safe to work on. Confirm that the circuit is de-energized. Use a non-contact voltage tester to verify that there is no voltage present at the breaker terminals. This is an important step to ensure your safety. Remove the old breaker. Use a screwdriver to loosen the screws that hold the breaker in place. Carefully remove the breaker from the panel. Install the new breaker. Align the new breaker with the bus bars in the panel and snap it into place. Tighten the screws to secure the breaker. Restore power to the circuit. Turn the main breaker back to the on position. Test the new breaker. Turn on the air conditioning units and observe the breaker for any signs of tripping. If the breaker trips, there may be another problem with the circuit. Breakers are designed with specific trip curves, which define the relationship between the magnitude of the overcurrent and the time it takes for the breaker to trip. These trip curves are carefully engineered to protect the electrical system from damage without causing unnecessary disruptions. Different types of breakers have different trip curves depending on the application. For example, some breakers are designed to trip quickly under high overcurrent conditions, while others are designed to trip more slowly to allow for temporary overloads. The type of breaker used in a particular application should be selected based on the specific requirements of the system. Electrical codes and standards provide detailed guidelines for selecting and installing breakers. These codes and standards are designed to ensure the safety and reliability of electrical systems. It is important to be familiar with the applicable codes and standards when working with electrical systems. Regular maintenance and inspection of electrical systems are essential for ensuring their continued safety and reliability. Breakers should be inspected periodically for signs of damage or wear. Wiring connections should be checked to ensure that they are tight and secure. Any potential problems should be addressed promptly to prevent them from escalating into more serious issues. Furthermore, consider the impact of ambient temperature on breaker performance. Breakers are typically rated for operation within a specific temperature range, and their performance can be affected by extreme temperatures. High ambient temperatures can cause breakers to trip at lower current levels, while low ambient temperatures can cause them to trip at higher current levels. When installing breakers in areas with extreme temperatures, it is important to select breakers that are specifically rated for these conditions. Additionally, consider the altitude at which the breakers will be installed. Altitude can affect the dielectric strength of air, which can impact the performance of breakers. At higher altitudes, the air is thinner, which reduces its dielectric strength. This means that breakers may be more likely to arc or flash over at higher altitudes. When installing breakers at higher altitudes, it is important to select breakers that are specifically rated for those conditions. Coordination between breakers is also crucial for maintaining system reliability. In a properly coordinated system, the breaker closest to the fault will trip first, isolating the fault and preventing it from spreading to other parts of the system. This coordination is achieved by carefully selecting the trip curves of the breakers in the system. It is important to ensure that the breakers are properly coordinated to minimize the impact of faults on the electrical system. Surge protection is another important consideration for protecting electrical systems. Surges can be caused by lightning strikes, switching operations, or other events. These surges can damage or destroy sensitive electronic equipment. Surge protective devices, or SPDs, are designed to protect electrical systems from surges by diverting the surge current to ground. SPD should be installed at the service entrance and at other critical locations throughout the system. Grounding is another essential aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to ensure that breakers will trip quickly and effectively in the event of a fault. Grounding also helps to reduce the risk of electrical shock. It is important to ensure that electrical systems are properly grounded in accordance with applicable codes and standards. Arc fault circuit interrupters, or SIs, are another important safety device for protecting electrical systems. SIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when wires become loose or damaged, or when appliances malfunction. SIs trip the circuit when they detect an arc fault, preventing a fire from starting. SIs are required in many areas of the home, such as bedrooms and living rooms. Ground fault circuit interrupters, or GFCIs, are another type of safety device that is designed to protect people from electrical shock. GFCIs trip the circuit when they detect a ground fault, which is a condition where current is flowing through an unintended path to ground. Ground faults can occur when appliances come into contact with water or when people touch live wires. GFCIs are required in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor areas. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical installations. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It is important to be familiar with the NEC when working with electrical systems. Electrical safety training is essential for anyone who works with electrical systems. Electrical safety training teaches people how to identify and avoid electrical hazards. It also teaches people how to properly use electrical equipment and how to respond to electrical emergencies. Electrical safety training can help to prevent electrical accidents and injuries. When working with electrical systems, it is important to always follow safe work practices. This includes wearing appropriate personal protective equipment, such as gloves and eye protection. It also includes using insulated tools and equipment. Always de-energize circuits before working on them, and always test circuits to verify that they are de-energized. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician. An electrician has the knowledge and experience to safely and effectively install, repair, and maintain electrical systems. Remember to consult local electrical codes for proper installation requirements. These codes are in place to ensure the safety of the electrical system and the people using it. Ignoring these codes can lead to dangerous situations and potential fines. Always prioritize safety when working with electrical systems. Electricity can be dangerous, and it is important to take precautions to protect yourself and others. By following safe work practices and using appropriate safety equipment, you can minimize the risk of electrical accidents and injuries. Before starting any electrical work, make sure to properly identify all the circuits and components involved. Labeling wires and breakers can help to prevent confusion and mistakes. Use a circuit tracer to identify the specific circuit that you are working on. This will help to ensure that you are de-energizing the correct circuit. When working with electrical systems, it is important to use the right tools for the job. Using the wrong tools can damage equipment or create a safety hazard. Use insulated tools that are specifically designed for electrical work. These tools are designed to protect you from electrical shock. Avoid using metal tools near live electrical circuits. Metal tools can conduct electricity and create a shock hazard. When working with wires, use wire strippers to remove the insulation without damaging the wire. Use crimpers to make secure connections between wires and terminals. When working with electrical panels, be careful not to touch any of the live components. The bus bars in the panel are always energized, even when the main breaker is turned off. Use a non-contact voltage tester to verify that there is no voltage present before touching any component. When installing new electrical equipment, be sure to follow the manufacturer's instructions carefully. The manufacturer's instructions will provide important information about the proper installation and operation of the equipment. Before connecting any new equipment to the electrical system, make sure that it is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect against electrical shock. When replacing a breaker, be sure to select a breaker that is properly rated for the circuit. The breaker rating should match the wire size and the load that the circuit is designed to carry. Using a breaker that is too small can cause it to trip frequently, while using a breaker that is too large can allow the wires to overheat and cause a fire. When working with electrical systems, it is important to be aware of the potential hazards. Electrical shock, arc flash, and explosions are all potential hazards that can occur when working with electricity. Take precautions to protect yourself from these hazards by following safe work practices and using appropriate safety equipment. If you are not sure how to perform a particular electrical task safely, it is best to consult with a qualified electrician. An electrician has the knowledge and experience to safely and effectively perform electrical work. Regular inspections of electrical systems can help to identify potential problems before they become serious. Electrical inspection should be performed by a qualified electrician. The electrician will inspect the wiring, breakers, outlets, and other components to ensure that they are in good condition and that they are properly installed. If any problems are found, the electrician can recommend repairs or replacements to ensure the safety and reliability of the electrical system. Consider the load calculations for the air conditioning units. Ensure that the existing electrical service and panel have sufficient capacity to handle the combined load of all the units. If the load is too high, it may be necessary to upgrade the electrical service or panel. Check the wiring connections to the air conditioning units. Loose or corroded connections can cause resistance, which can lead to overheating and voltage drop. Make sure that all connections are tight and clean. Consider the use of surge protection devices to protect the air conditioning units from power surges. Power surges can damage or destroy electronic components in the units. Surge protection devices can help to prevent this damage.